All right, so yesterday we talked about synthesis of amines, and one of the ways we can make amines is through this azide synthesis. However, I ended by saying the big drawback to this is it could kill you. The lethal dose of sodium azide is about 0.7 grams. It will get absorbed through your skin. If you're doing this on a large commercial scale, that is incredibly dangerous and silly. So, chemists wanted to devise a better way that doesn't involve some crazy toxic compound. And they were able to accomplish this through a new reaction called the Gabriel synthesis. Oh no. Oh. Sorry guys. I'm going to close it and reopen it. I think the cord might be frayed here or something. I need to request a new one. All right, so the Gabriel synthesis is an alternate route through which you can make an amine from an alkyl halide. But the key thing is it avoids toxic reagents like sodium azide that we just saw. So let's take a look at the overall reaction. And the overall reaction is pretty straightforward, but it does involve a kind of funky looking reagent. This is referred to as phthalimide. It's commercially available, very cheap. You can buy big bottles of it, no problem. It won't kill you. And then the first thing you're going to do is you're going to treat this with a base, usually sodium hydroxide or potassium hydroxide. Then you're going to treat it with some sort of alkyl halide. And then, depending on the textbook that you see, you'll either do a hydrolysis using acid, or you'll treat it with hydrazine. And the reason you'll see both is this one is very slow right here, and the hydrazine is very fast. Typically, more modern labs will use the hydrazine. However, hydrazine itself is toxic and very flammable, so it really depends. So the products that you'll get out of this are going to be your amine. So that alkyl halide will turn into an amine, and then your byproduct is going to be one of two things. It's either going to be the diacid, and this is if H3O is used. It's pretty innocuous. Oh my goodness. Or, come on. Sorry guys. Here we go. Or it will be the derivative if you use hydrazine. And you have to pay attention to which product will come out depending on your workup conditions. Does that make sense, the two different byproducts? Let's go through and do the full mechanism though. The full mechanism I think is pretty important, but it's pretty easy at the same time. So the first thing we're going to do is treat it with sodium hydroxide. So what do you think is going to happen to our starting material? Yeah, deprotonate it. Do you think we're going to deprotonate one of the benzene protons or the nitrogen one? Nitrogen. So it's not a great reaction. Normally the pKa of amides isn't that low, so it's not a very acidic proton, but there is going to be some of it that gets deprotonated under equilibrium conditions. So now this nitrogen would have 2 lone pairs. We'd have water as a byproduct. And then in the next step, we're going to treat this with our alkyl halide, which is a good electrophile, so our nitrogen can attack in and kick off our leaving group. All right, and so now we're at this intermediate. And like I said, if you treat this with acid and heat, you're basically going to convert that amide all the way to a carboxylic acid. Oh, my goodness, come on. Not today. It's too hot to deal with this. Come on. All right. Sorry. So we get our dicarboxylic acid, and then we get our amine, which in this case is actually going to be your protonated amine. And why are we going to get our protonated amine out? Acid. Yeah, we've got it under acidic conditions. So the last step we would need to do would be to treat this with some sort of weak base. Typically, you can do this using a variety of conditions. It really depends on the amine that you're working with. Usually you want something more basic than water, because amines are more basic than water, right? So you want something that will pluck that proton off. Alternatively, we said the faster route is to use hydrazine. Where you get the same sort of nucleophilic acyl substitution. And I'm not going to go through the full mechanism, and then you get your amine. And luckily with this one, you don't have to worry about a workup because you're not under acidic conditions at all. So in many ways, this is a nicer, easier reaction to do. However, like I said, it involves the use of hydrazine, which used to be used as a rocket fuel. So something you've got to be a little bit careful with. Does that make sense? Let's do some synthesis practice. All right, so let's propose a synthetic transformation where we start out with this hydrocarbon. And then we go to this primary amine. I'll give you guys a minute to work on this and then check with your neighbor to see if you got it. Like I said earlier this year, I always recommend going backwards. What do you think the precursor should be before the final product? Yeah, so I'd say maybe some sort of halogen. There, so I'll just call that an X. All right. Then the question is, well, how can we get the halogen on there? Close. If we did a radical halogenation, we would probably halogenate the more substituted carbon, right? One of the tertiary ones. So that might not work super well for this step. What's another intermediate we could have? An alkene, right? We could do anti-Markovnikov halogenation, or hydrohalogenation, I should say. Okay, and then the question is, well, how could we make this alkene?
By having a bromine and then O2.
So some sort of elimination reaction? I think that makes sense. Okay, then the question is, well, how can we get from here to here? Radical halogenation. So for this one, radical halogenation is a really direct route. So now what we need to do is fill in the reagents. So radical halogenation, what do we need? Br2 and UV. I agree. All right, so I'll pop in a bromine here since we know we're doing bromination. Why don't we want to do chlorination?
It's less
It's less selective. It would over-halogenate. It wouldn't care which carbon it halogenates. All right, next step, we want to do an E2 reaction, but we want it to be a Hofmann product, right? Not a Zaitsev. So what are we going to use? Big bulky base. So again, you can't forget about Hofmann versus Zaitsev for that E2 reaction. You want to use a big bulky base, give you the less substituted alkene. All right, then the next one, anti-Markovnikov hydrohalogenation. What should we use? Yeah, HBr and peroxides. That was a reaction we covered last term. I will put the bromine on there. Whoops. And then last but not least, what do you guys want to use for installing the amine? What's that? Not ammonia. We said ammonia. If you try to do SN2 chemistry, you run into over-alkylating it. You don't stop at your final product. What was one of the other alternate routes? We could do sodium azide. We said that might kill you. Gabriel synthesis is a better route. All right. So step one would be to treat this with phthalimide, ideally deprotonated phthalimide. So I'm going to say, you know, we're going to make this by treating this with hydroxide. And then step two, what do we want to use? The hydrazine? Yeah, hydrazine's nice and fast. It's a two-step reaction for that last step. So the number one mistake I see people make is not to point fingers at you, Marcus, but oftentimes students will say, throw in ammonia, right? Why won't it do SN2 chemistry? Problem is that over-alkylation problem is a huge complication. So you have to use something like the Gabriel synthesis or the sodium azide reaction to get this to stop at a primary amine.
Even if it's this bulky of a carbon.
Even if it's that bulky of a carbon, yeah. All right, so now we need to cover ways to make secondary and tertiary amines. Right now we're kind of stuck with primary amines because we're doing SN2 chemistry. So I'll show you guys a new reaction. And the new reaction is pretty clever. And I'll show you guys the overall idea. What's that? You don't use ammonia. You take some sort of ketone and aldehyde, or aldehyde. And then what happens? Well, actually, I'm wrong. You are going to use ammonia for the first step, at least for this one. What happens if you treat this with ammonia and drive off water? What will you get? Are you going to get an enamine or an imine? An imine, right? So where's the double bond going to be for an imine? Yeah, between the nitrogen and carbon. So I'm going to show the protonated version. This is our iminium ion, where that nitrogen still has its proton. In equilibrium, it will be in, it'll exchange with the imine itself, the neutral one. And then the next step is really straightforward. We're going to do a reduction. And if you do a reduction, you're going to take that carbon-nitrogen double bond, and you're going to convert it to a single bond. The neat thing with this is you can use this to make primary, secondary, or even tertiary amines. And the big thing is identifying reducing conditions that will work well and not react with other portions of your molecule. So let's make a note of this. Hydride reduction using LAH or NaBH4 can theoretically be used. But are problematic. you run into unselective reduction. It can reduce other aldehydes and ketones in your molecule, and I'll show you guys in a second why it doesn't work super well. So let's take a look at this iminium ion and compare it to its standard aldehyde or ketone. Which one do you think is going to be more electrophilic? What do you guys think the one on the right is going to be more? It's got a full positive charge, right? And that carbon, if we think about it, has a resonance structure where you can kick up electrons onto that nitrogen. Oh, my goodness, don't do this. Sorry, I'm going to take this cord into the IT department and get it swapped out. There's a resonance structure where you can delocalize that positive charge down to that carbon. So this carbon is way more electrophilic. All right, so now let's compare our reducing agents and find one that's...
Wouldn't we also have to consider the protonated ketone?
Yeah, so in this case, if you wanted this one to be more electrophilic, you would have to protonate it. But the iminium ion, because it's a nitrogen, is a lot easier to protonate than an oxygen. Nitrogens are more basic than oxygens. Okay, so now let's compare our reducing agents that we've seen. What's our most powerful reducing agent? Right, that's the strongest oxidizing. Yeah, LAH. Lithium aluminum hydride, we said is super duper strong, followed by what? NaBH4. Reducing agents. And then we'll put weaker down here. There's a new one called sodium cyanoborohydride, where it's NaBH3CN. It's actually not. It's really easy to work with. And why do you think this isn't as strong of a reducing agent? Yeah, nitriles, we said, are strong electron withdrawing groups, right? So through induction, you can pull that electron density away from this negative charge and help stabilize it somewhat. So for the reducing conditions we're going to be seeing, we're going to be using this sodium cyanoborohydride. So let's go back and use this in our reduction scheme. So let's say we've got our ketone. And we said step one, you're going to treat it with your buffer solution and ammonia. You're going to drive off water. You're going to form your iminium ion. And then we're going to reduce this using NaBH3CN. That's the sodium cyanoborohydride. And you can get straight to this primary amine. Works pretty well. The coolest thing with this reaction is I showed this as two separate steps, but you can actually do this all at once. So let's go ahead and kind of condense everything down. And I'll show you the overall reaction scheme. there we go.
You do the water.
Yep, so water is going to be treated as a leaving group. You don't have to include it above the arrow or below the arrow unless you really want to. All right, so going back to our original question, why can't I use a different reducing agent? Why can't I just throw in lithium aluminum hydride? It's not selective, so if you've got other functional groups, it might react with those. What's another reason? Lithium aluminum hydride's like a bowl in a china shop. It'll reduce that ketone before the amine even has a chance to form. So instead of getting your amine, you get an alcohol. It'll outcompete that amine formation. So let's make a second note of that. Can't use other reducing agents. Or else it will reduce your amine, or sorry, reduce your ketone. Oh, shoot. Your ketone or your aldehyde before it can form your amine. Does that make sense? Okay, so I'll show you guys some cool reactions based off of this, but before we do, let's make a little chart. This is arguably the most versatile reaction from this chapter. We can make primary amines. We can make secondary amines, or we can make tertiary amines using this technique. For the top one, we already saw that example where we said all you would need to use is NH3, treat it with some acid, and then do sodium cyanoborohydride. For the next one, you would want to use a primary amine. Oops, it should be H2NR, catalytic acid, and sodium cyanoborohydride. Then for the last one, you'd want to use a secondary amine. So the previous reaction we saw could only be used for primary amines. This one's way more versatile. And to be honest, it's pretty popular. However, I will explain in a little bit one major downside to it. But before we do that, let's take a look at some fun pharmaceutical chemistry. So let's take a look at this compound, and I want you guys to help me determine what the, oh my goodness, what the final product should look like. So we've got a benzene ring, 6-membered ring, ketone up here, we've got a wedge, another benzene, and then 2 chlorines that are ortho to one another. And I'm going to treat this with methylamine. What product do you think we're going to get out? Is it going to be primary amine, secondary amine, tertiary amine? What am I missing? Okay, so we need the nitrogen. Is it an NH2? Yeah, it's going to have a methyl group. And we will still have one of these hydrogens coming off. And there we go. One thing to note is we are forming a new stereocenter, so this is going to be a racemic reaction. There are stereoselective reductions, however, they aren't covered in this book. And this is Zoloft. Zoloft is one of the best-selling drugs in the United States, and this is actually how they do one of the final steps. One interesting thing with these, I'm going to highlight this, is you'll oftentimes notice the same functional group showing up again and again in these types of drugs. You've got an amine adjacent to a benzene ring. There's a whole class of antidepressants based off of these and recreational drugs that are based off of these, which is a huge problem because this chemistry is super easy to do. You can do it in one pot, and you can do it after taking 3 terms of organic chemistry. So, I can't get in trouble for showing you this next one because it's in your textbook. But how many of you guys have seen Breaking Bad? All right, so I'll show you guys the Breaking Bad synthesis. What's the name of this compound? So identify the longest carbon chain and treat the benzene as a substituent. Oh. Question is, should I number going 1, 2, 3? No, I would go 1, 2, 3. Is this a phenyl group, a benzyl group, a benzene group? How do we name this as a substituent? Phenyl. This is something that's messed up a lot, is if you've got a benzene ring coming off of something, this is a phenyl. If you have a benzene ring with a CH2 spacer, this is a benzyl group. So this would be a phenyl substituent, not a benzyl substituent. I see that getting mixed up a lot. Okay, so now let's name this. So a phenyl group is when you have an aromatic ring like a benzene coming directly off of some sort of backbone, right? A benzyl group is when you've got this CH2 spacer and then a backbone. So this would be a benzyl substituent, this entire thing. This one is just a phenyl. Yeah. All right, so now let's name our starting material again. What should it be called? Yeah, you could say 1-phenyl, although it's implied. So phenyl 2-propanone. No, because it's a part of the backbone of your longest chain, you don't count that CH2 spacer. That's a good question. So because this CH2 right here is a part of the backbone, it's not considered a benzyl group. A benzyl group is when you have a CH2 and then a phenyl ring coming off of the backbone. So it really depends on how you identify your backbone, right? If that CH2 is a part of the backbone, it can't be counted as part of a benzyl group. Yeah. Okay, so if you're a fan of Breaking Bad like I am, you hear them refer to P2P a lot. It's phenyl 2-propanone. There's a scene where they go and steal a ton of it. Pretty interesting stuff. And then there's another scene where they steal a bunch of methylamine out of a train car. So they steal a bunch of methylamine. They don't use these reducing conditions. They use a different set of reducing conditions. They actually use I'm trying to remember, it's like some sort of mercury aluminum amalgam in order to do their reduction. So you see them dumping mercury into the tanks a bunch. And when you do this, you end up making meth. So people always ask me, like, oh, does that mean you can make it? The problem is all of these precursors are so highly regulated. If you went to try to buy something like this, the DEA wouldn't be knocking at your door in about 3 minutes. So this isn't at all something anybody should experiment with. It's a really big problem. If you're interested at all, there was a fascinating documentary on Nova a few years ago talking about the meth epidemic, primarily in Oregon. There were towns completely ravaged by this stuff. It's a super nasty drug that nobody should ever play around with. Spokane's bad. A lot of times when you go east of the Cascades, you run into these communities that have just been destroyed by meth. All right, so let's take a look at one. So proposes synthesis. And I'm going to give you guys a funky looking one. So try to use reductive amination, just like we've been doing, to make some sort of route for making this product. How many people feel like they got this? All right, I'll show you guys a hint based on this one. Based on these top two, I should say. So if we look at these top two, really what we're looking at is a CO bond, CO double bond right here that got converted to a CN single bond, right? So if you see a CN single bond, you could deduce that maybe that used to be a CO double bond before the reductive amination, right? So let's go back and take a look at this one. We've got a bunch of CN single bonds, right? We've got one right here. We've got one, let me change colors, right here. And then last but not least, we've got one right here. So any one of those positions could have been a CO double bond at one point in time, right? So let's just pick them arbitrarily. I'll use the blue one first. So this is my arrow for going backwards, my retrosynthesis arrow. Oh, let me clean this up a bit. So maybe that's what it used to look like. Does that make sense? So that could be one of our starting materials. Let's do the green one. Would it be the same? Oh. Yes, no, maybe. I don't know.
Put that on an exam, I think you're in for that time.
So if we did the retrosynthetic analysis for that green position, yeah, you're right. These would be the exact same. All right, and then we'll do the last one. The last one looks kind of funny. But it would be this super big cyclic system. So which one do you guys want to pick? Yeah, let's just pick the blue one, for example. Okay. So let's go ahead and do the forward reaction. And we've got 1, 2, 3 carbons, right? And then we have an aldehyde. Okay. And then next step, we need to treat this with what? Do we need to throw in any amine? Why not? Yeah, it's an intramolecular reaction. And now you can make your bicyclic ring system. And it works nice and easily in one step. So the first step is you make that enamine in this case, and then you can reduce that using sodium cyanoborohydride. All right, I think that's where we're going to stop today. For the pod that I handed out, what I want you guys to do is to read ahead a little bit in the textbook to the section that talks about diazonium salts. We've already seen these reactions before for the azodi lab, so you guys should be kind of familiar with it. But try to go through the book, find the mechanism, and then work through the pod with a teammate or a classmate.